Welcome my friends, welcome to my next lecture. Now I am almost at the end of this course. So only the last topic is remaining to talk about the concept called or the notions of Gauss theorem and Stokes theorem. So this is the last concept in this course. So I need maybe 2 or 3 lectures to complete it. So that is the end of this course structure, whatever we have kind of promised at the beginning that we will discuss. So I need couple of lectures to complete it. So the last concept is to talk about the notions of Gauss theorem and Stokes theorem. Now to do that I need again some concept of what is called surfaces that I already discussed when I talked about what is called vector scalar surface integral and vector surface integral, if you remember. So what my plan is to talk about, again recall the notions of surfaces like smooth surfaces and oriented surfaces, and then I will go for the statement of Gauss theorem and Stokes theorem and couple of applications or couple of problems concerning Gauss theorem and Stokes theorem. I will talk about that. Okay, so right, so this is the learning outcome as I have written. So this is first I will start with like surfaces and oriented surfaces. I will just recall. So those kind of concept I already discussed in my last couple of lectures when I talked about what is called scalar surfaces integral and vector surfaces integral. There I started with the notions of surfaces and oriented surfaces, and those kind of concept I have already discussed. First I will start with recalling all those definitions once again. Okay, then I will talk about oriented boundary curve. So if I have a oriented surface, then that oriented surface will induce automatically some orientations on the boundary. Okay, so once I have these two concepts, then I will talk about what is the statement of Stokes theorem, some example I will talk about, and then I will talk about idea for extending Stokes theorem to surfaces with like not nice surfaces, that means surfaces with holes, and then at the end I will talk about what is called Gauss theorem or divergence theorem and some examples. Okay, so as I said, so let me just recall the definition of surfaces. So what is the definition of surfaces? That you know that a surface S may be thought of as a graph of a continuous functions from a rectangular region or a simple region R in the plane. So that means you can think about that a surface is, I can think about as a graph of a functions, graph of a continuous functions. What is the functions? Functions defined on some nice region. Okay, that's why I am writing. Either it should be rectangular region or simple region, right? You know, simple like horizontally simple or vertically simple, that kind of region I talked about in my again last couple of lectures. So if I have a continuous functions A which is defined on very nice region like rectangular region or simple region, that I am denoting as R, subset of R2 and taking values in R3. So then the graph of this function is called the surfaces. For example, if I consider this kind of functions, so like it's a function, so G is a map which is Z is equal to G of xy. So what is a xy running over R? So it is a nice region in R2. Then I am saying that surface S, which is of course subset of R3, it is a collection of all those x, y, z in R3 such that xy running over the region R in R2 and the third component Z which is given in terms of functions of x and y, which is nothing but Z is equal to G of xy. So then this set S represents a surface in what is called R3. Another example, so like if I start with a nice region R where xy belongs to R2, where x running from 0 to 1 but y runs from 0 to 1 minus x. Now if you recall this kind of region where x varies from some fixed number to some fixed number, however y varies from some function to some function, it's a function of x, right? So this kind of region, if you remember, it is called vertically simple regions. It looks like kind of thing. So this is x fixed and something like that. So y varies from these two. So this kind of region is called a vertically simple region, right? So now if in R I have a nice region like say, that's why I said simple region like vertically simple region, and then I am saying that okay, the surface is nothing but, so it is the collection of all those x, y, z where x and y running over this region R and z is written in terms of 1 minus x minus y. So that means what is my surfaces or subset of R2? This should be x comma y comma 1 minus x minus y. So that means z is given as a function of gxy and gxy is nothing but 1 minus x minus y. Okay, so that will be an example of what is called surfaces in R3. So this is another way you can think about the surface. A surface S can be thought of the level surfaces of my function g of x, y, z is equal to 0. So that means you know the concept of level surfaces, I already discussed in my long before lectures. So are surfaces that one can also think about as the level surfaces of my function g of x, y, z. For example, if I consider say g of x, y, z is equal to x square plus y square plus z square minus 1. Okay. Now g x, y, z is equal to 0 means what? X square plus y square plus z square minus 1 is equal to 0. That means it will give you the what kind of surface it will be? That means x square plus y square plus z square is equal to 1. That means what? That means it will be a unit sphere. Okay. So that is another example. And this is just the collection of all those x, y, z, where g of x comma y comma z is equal to 0. That is nothing but the level surfaces. And here what is my function g of x, y, z? Here in the last example, g of x, y, z is nothing but x square plus y square plus z square minus 1. Okay. In this way you can think about the surface. A surface can be thought of as the level surfaces of my function g of x, y, z is equal to 0. Okay, surfaces, though again you can think about in many ways. You can think about surfaces. Another one is that locus of a point moving in a space with 2 degrees of freedom, that also in that way also you can think about. So then again you can think about like start with a scalar field, like start with a functions f from some domain d subset of R3 to R. Okay, so start with a scalar field. So then for example, this kind of x square plus y square plus z square is equal to c and z is equal to x square plus y square. So these are the kind of, so like surfaces, of course, though I am saying actually level curve. So that means though I am talking about the vector field f from R3 to R, so the level curve of this scalar field will give you a surface. For example, this kind of functions like if it maps from D subset of R3 to R, one is this x square plus y square plus z square is equal to c, or you can think about that x square plus y square minus z is equal to 0. So these are the scalar field and that will be the level curve of this scalar field and this will give you a surface. Okay. What about number 3? Sometimes surfaces can be described, again same thing I am telling again and again. So it is the collections of all those x, y, z, where x, y runnings over D subset of R2 and z you can write in terms of x and y, function of x and y. In my last slide I said that z is equal to g of x, y, where g is nice. So this is okay. So if I have this kind of representation, this is called the explicit representation. So explicit representation means it is a collections of all those x, y, z, where x, y runs over R2, so that means some nice region in R2, and z is nothing but a functions of x comma y. So that I am saying that z is equal to f of x, y. If a surface represented in this way, this is called the what is called explicit representation. Okay. Second, so first one is the locus of a point moving in a space with 2 degrees of freedom. Second one is the level curve of a scalar field. Take a scalar field, consider the level curve, this will give you the surfaces. Third one is the sometimes surfaces in the explicit form. Explicit form or explicit representation means it is the collections of all those x, y, z in R3 where x comma y runs over a very nice region in R2 and z you can write in terms of functions of x and y. That means z is equal to f of x, y. So for example, I can write unit sphere. I already have the unit sphere like what is called level surfaces of this function g of x, y, z, which is x square plus y square plus z square minus 1. If I have g of x, y, z is equal to 0, so that is the corresponding surfaces unit sphere. Now the unit sphere I can also think about as a union of two such explicit representation like this one. So like that means I can write, so unit sphere, which I know that the collection of all those x, y, z where x square plus y square plus z square is equal to 1, that I know, that I can write as a union of two explicit representation. What? So this is what collection of all those x, y, z where x and y they satisfies that x square plus y square less or equal to 1. However, z I can write in terms of x and y, that means z is equal to square root of 1 minus x square minus y square. Union x comma y comma z, that means it is nothing but minus of this object. So that means you can have a sphere like, so the first one will give you the upper hemisphere and second one is the lower hemisphere. So that is union of two explicit representations of the given sphere of radius 1, you can have it because you have x, y varies from x square plus y square less or equal to n in the 2 dimension, but z you can write in terms of x and y, which is nothing but square root of 1 minus x square minus y square. Plus stands for the upper hemisphere and minus stands for the lower one. Together it will give you the full sphere of radius 1. Okay. There is another representation what is called parametric representation of a surface, like parametric representation of a curve, and you know, so simply you can have a parametric representation of a surface. So a surface may also described in terms of, because I am talking about surface in R3, right. So it says that suppose your small x is a functions of u and v, small y is some functions of u and v, and small z is some functions of u and v, where uv runs over d and d is a connected subset in the uv plane. For example, plane, what kind of region, like it's say the like region like circle, rectangle, or say vertically simple or horizontally simple. That means nice region I am talking about in R2, so that your small x, small y and small z can be written as a functions of u and v. If I represent my surface in this way, then I will say that this is the corresponding parametric representations. Okay, so this is the definition I am saying. So a continuous functions capital R, which is a map from some nice domain subset of R2 taking values in R3, is called the parametric surface in R3. The image of my domain D under the map R, if I denote it as S, is called the geometric surface in R3. So therefore, if I have a continuous functions R, which is nothing but a parametric representation of my surfaces, it is a nice function, that means continuous function from set D, which is subset of R2 to R3, then if I consider the image, this is called the geometric surfaces. Okay. Now look, if the surfaces has an explicit representation, now explicit representation means what? It is a collection of all those points x, y, z, where z can be written as a function of x, y, right? So that means x, y, f of x, y or g of x, y, depends, right? So therefore, if the surface has an explicit representation given by a continuous function, say z can be written as a function of x and y running over D, then what is my parameterization? So that means I can write R of x, y. See, if the first component is x as it is, second component is y, and third component was z. Now z can be written as f of x, y. So therefore, this is the corresponding what is called parametric representation. So therefore, if I have a explicit representations of my surfaces given, then you can easily write its parametric representations, and very easy, because you can write that your parametric representation R, which is a map from some nice domain D subset of R2 to R3. What are the points in R3? That means if R acting on x, y running over your nice domain D in R2, then in the value should be in R3. So what is the first component? First component should be, because explicit representation means what? It is a collection of all those x, y, z, where z can be written as some functions of x and y. Nice function, continuous function here I have written. So therefore, the first component should be x, second component should be y, and third component you can write f of x, y. So therefore, if a surface has a explicit representation, then automatically you can write the parametric representation in this way. Okay, so that is what. Like for example, if I talk about the parametric representations of a sphere of say radius a, suppose you have a sphere in three-dimensional Euclidean space, and suppose with the radius a, then what will be the corresponding parametric representations? Then spherical representation, if you see. So now if you take the spherical coordinates, then you know I already discussed, you can write your component small x, small y, small z, that means the Cartesian coordinate, in terms of theta and phi. That I am written as capital X of theta comma phi, which is a sine phi cosine theta. The coordinate y can be written as capital Y of theta comma pi, which is a sine phi sine theta, and z can be written as z theta pi, which is a cosine of phi. But here phi should varies from 0 to pi and theta should varies from 0 to 2 pi. Okay. So if I have this kind of representation, then this gives a parametric representation of my sphere. What is my representation? That means this is my capital R. Capital R is a function of phi and theta, where phi varies from 0 to pi, theta varies from 0 to 2 pi, because you see phi theta varies in the two-dimensional plane, and this is since phi varies from 0 to pi and theta varies from 0 to 2 pi, that means it is actually a kind of square region. It's a very nice region in R2, and it's taking values in R3. So first component is a sine phi cosine theta, second component is a sine phi sine theta, and third component is a cosine of phi. Now if phi and theta varies in this region, then you can see it will produce a surfaces in R3, and this is called the spherical representation. And once I have a spherical representation, then this is the corresponding parametric what is called representation of my surfaces. So this is called parametric representation of a surface of radius a. So that means your map, that is parameterization map capital R, is a map from what is called some square subset of R2. What is the square? 0 to pi cross 0 to 2 pi. This is the region 0 pi cross 0 to 2 pi. That is the region in R2 to R3, taking values whose first component is a sine phi cosine theta, second component is a sine phi sine theta, and third component is a cosine phi. So this is gives the what is called parametric representations of my given surface of radius a in R3. Okay. So this is called spherical coordinate system. So that means you can write your Cartesian coordinate system in terms of theta and phi, right? Okay. Another one, like if I want to talk about parametric representation of a cone, suppose you have a cone, okay, in the R3. So what will be the parametric representation? Now we find a parametric representation of the cone. Now this is what? Z is square root of x square plus y square, and z running from 0 to 1, right? So therefore now it is what? So this is actually given in the what is called explicit representation of your surfaces, which is nothing but a cone. Now you know the concept called cylindrical coordinates. So here cylindrical coordinates provide everything what we need actually. What is cylindrical coordinates? That means I can write my Cartesian coordinate x, y, z in terms of functions of r and theta. So now x I can write as a function of r and theta, which is nothing but r cosine theta. Y, the coordinate I can write as a function of r and theta, which is r sine theta, and z as it is. Z is given square root of x square plus y square, which is nothing but x is r cos theta, y is r sine theta. So this is equal to r. So therefore each Cartesian coordinate x, y, z I can write in terms of r and theta, right? And where r runs from 0 to 1 and theta runs from 0 to 2 pi. Again you see, so r and theta running in a square region in R2, which is very nice, taking values in R3, whose first component is r cosine theta, second component is r sine theta, and third component is r. So this will be the corresponding what is called parametrizations of my cone. So therefore capital R is the parametrizations which acting on small r and small theta, it should be r cosine theta I cap plus r sine theta j cap plus r times k cap, where r runs from 0 to 1 and theta runs from 0 to 2 pi. So therefore if we know the cylindrical coordinate system, that means if I know the relations between Cartesian x, y, z to the functions of r and theta, where r runs from 0 to 1 and theta runs from 0 to 2 pi, that will induce what is called parametric representations of my cylinder, and which is nothing but this one. Okay. So now you know, so given spherical coordinate system, it will give you a parametric representation. Given cylindrical coordinates, it will give you a parametric representation of your cone. Okay. Okay. So this is very brief about your surfaces, right? Like definition of surfaces, couple of examples, couple of ways you can think about surfaces. Now I come to the notions what is called smooth surfaces. What is smooth surfaces? So smooth surfaces, again, whenever I'm going to talk about some surfaces, now I am restricting myself in R3, not higher dimensions. Okay. So now smooth surfaces. Now you know the definition of surfaces I already explained. Now it will have a parametrizations, right? Now once I have a surfaces, and if I know the parametrizations, then I can talk about what is called smooth surfaces. What is that? Look, let capital R, which is be a region in R2, suppose it satisfies two properties. What are the properties? First one, R is suppose convex and bounded region in R2. And number two is that I need special kind of region, that is very simple region. That means either it is vertically or horizontally simple region in R2. So that means R has two properties. So R is either vertically and horizontally simple region in R2, along with that R is convex and bounded region. Okay. If I have two properties of my R, then let 5 wave functions with domain R sitting inside R2 to R3, and what is the map? Phi of u comma b, suppose u be my variables in the region R subset of R2. Suppose it maps to what is called first component is small x u v, second one is small y y b, and this is function of u and v. So that means the corresponding coordinate system x y z I can write x u v, y u v, and z u v, where u v runs over R, such that it is a parameterization, right? I just talked about. So if the corresponding functions phi, which defines in this way, and if it is continuous, so it will give you some surfaces in R3. I know that these surfaces should be smooth. I need some extra assumption. What is that? First of all, phi should be continuously differentiable. Now continuously differentiable I already discussed, that means function should be differentiable. Not only that, derivative should also be continuous, that is called continuously differentiable. That means I demand that this parameterizations phi of my surfaces in R3, it will induce some surfaces, that functions phi should be continuously differentiable. That means each of the component functions should be differentiable and they are continuous, number one. Number two, phi should be injective except possibly on the boundary. Now if I have a region R in R2, so it will have a boundary region denoted by delta of R. Now if I look at the interior region bounded by this delta of R, that means boundary of R, in that interior region my function should be injective or 1 1. And what is the third one? Third one is that at each point P in R, so that means in the domain, if I take a point P in R, then I can define what is called normal vector in the surfaces. What is that? This is called phi up cross phi b. What does it mean? That means I am talking about del phi del u at the point P cross product with del phi del v at the point P. Okay. So this is the vector should be non-zero vector. That means at each point P in my domain, the corresponding normal vector. So that means phi, if I take a point P in R, So the range will be phi of p, right. So since it is a surface, at that point I want to talk about the normal vector. What is the normal vector? This is the normal vector. That means del phi del u you have to calculate at the point p, and you have to take the cross product with del phi del v at the point. Now what is del phi del u? So that means this is phi is nothing but this component, na. So phi is your x of uv, y of uv and z of uv, right, that you know. So what is del phi del u? So del phi del u you can calculate at the point p, which is nothing but del x del u, okay, at the point p, comma del y del u, del y del x del u, right. Yes, so that means del y del u at the point p and del z del u at the point p. And what is del phi del v? This is again del x del v at the point p, comma del y del v at the point p, and this del z del v at the point p. Okay. So now I have two vectors. One is phi suffix u of p, that means del phi del u at the point p, cross product with del phi del v at the point p, and that vector should be a non-zero vector. That means at each point p in the domain, the corresponding there should be associated normal vector at the point phi of p, and this should be a non-zero vector. If my parameterizations phi satisfies these three properties, then the image, that means then the image of my region R under the map phi, if I denote it as S, is called the smooth surfaces in R3 with by parameterizations phi of uv defined on my region R, and it is simply called a parameterized smooth surfaces. So therefore, if I start with a very nice region, if I start with a functions phi which is defined on my region R subset of R2 to R3 in this way, and if it satisfies three properties. What are the properties? Number one, phi should be continuously differentiable, phi should be injective in the interior region bounded by what is called boundary of my region R, the interior region, it should be injective or 1 1, and if I take any point p in R, the corresponding normal vector at the point phi p in my surfaces, that should be non-zero vector. So some vector, that means the corresponding vector should be non-zero. Okay. Then the image, if I then once my parameterizations phi satisfies all those properties, so first two properties perfectly right. The third one, it says that take a point p in R, consider the normal vector which is nothing but del phi del u at p cross del phi del v at p. Okay, it should be a non-zero vector. If this is the case, then what you do, you call the set image of the region R inside R2 under the map phi, if I denote it as S, this is called the smooth surfaces with parameterizations phi defined over the region R, and it is simply called the what is called parameterized smooth surfaces. Okay. So let us see some examples. So examples of smooth surfaces. So that means I need to have a parameterization, and that function phi should satisfy all the properties. Okay, and that is first one is that the sphere. So x square plus y square plus z square is equal to 1. This is a unit sphere in R3. Now this has a parameterization. So I already talked about, like in terms of if I know the spherical coordinate system, you know the parameterization. So that means phi should be a map from 0 to pi cross 0 to 2 pi to R3. So this one runs over u runs over this one, v runs over this one, and what is the corresponding component? Sin u cosine v, sin u sin v, and this is cosine u. Coefficient should be 1 because I am talking about unit sphere, right? Now, what are the components? Look, the components are very nice. It is a combination of sine function and cosine function. They are infinitely many times differentiable. So therefore, it is continuously differentiable, number one. Second part is that it should be what? Injective in the open 0 pi or in the interval 0 to pi cross 0 to 2 pi, and that is also possible. Why? Because you just check it that if I take u and v different, two different points here, it should be injective, or we can talk about it, make the derivative, and you can conclude it. This is true. And third one is that if I consider any point p in my region 0 to pi cross 0 to 2 pi, you can have two vectors del phi del u and del phi del v at that point. If I take the cross product, it will give you a non-zero vector. Again, I am not going to do the calculations, but you just check it, it will satisfy all the three properties here. Continuously differentiable, perfectly all right. Just you have to check that it should be 1 1 in the interior region. That means if you kind of delete the boundary one here, what is the boundary one? That means you have to consider this interval 0 to pi cross open 0 to 2 pi. Okay. In this region, if I just check it, I think this function is actually injective. You prove it. That's I'm just giving as an exercise. You prove it. Okay. And what is the third one? Third one is that for each point, again, this should be non-zero. Again, you can calculate it because phi is given, right? Phi is given. You just calculate del phi del u and del phi del v at that point, and you just kind of consider the cross product. And you know, if I have two vector, how to calculate the cross product. Once you do that, then you will see that the corresponding vector will be non-zero. Again, I'm leaving as an exercise for that one. Okay. Another one is the hemisphere, that means the portion which lies in the upper plane. So like what is that? So it's a hemisphere, x square plus y square plus z square is equal to 1 with the fact that j should be, I am taking positive, that means it is x square. So what is the kind of explicit representation? That means it is the collection of all those x comma y, and here z should be plus square root of 1 minus x square minus y square. That means the upper portion I am talking about. Okay, is parameterized by the functions phi, r2, r3, and you know, if I have a surfaces which has a explicit representation, then it will have a parametric representation. And what is the parametric representation? Very nice, x comma y, and you should replace z by f of xy, and xy running over very nice region in R2. So that exactly I have done it. So this is the functions phi of xy, whose first component is x, second component is y, third component is z, which is plus sign is there because I am talking about the hemisphere where z is positive, then the upper one, and xy runs between r, and what is my r? R is x runs from minus 1 to 1, but y runs from minus square root of 1 minus x square to plus square root of 1 minus x square. I mean, this kind of region, if you see, x runs from some fixed number to fixed number, but y runs from some function of x to some function of x. That means that this region is actually a vertically simple region in R2, that means which is nice, and the corresponding parameterization is phi. You can think about that. Okay. So this is another smooth surfaces. Again, you can check it that these functions, of course, these are functions of x. This is a very nice function. These component functions are very nice. So it is differentiable. So therefore, your function is continuously differentiable. Again, you can check that it is injective and at the interior region of the R. And of course, if you check that if I take any point P in R, the corresponding normal vector, like means del phi del u at P, or del phi del x at P, and del cross del phi del y at P, it should be a non-zero vector. Again, I am leaving as an exercise and you complete it, please. And what about the third one? Again, third one, this is a cone where z is equal to square root of x square plus y square, and z runs from 0 to 1. Again, you know, if I have a surfaces which has explicit representation, then it will have a parametric representation. What is that? In terms of what is called cylindrical coordinate system, you know, so that means it is corresponding parameterization. So we parameterize S by the equations phi, which is a functions of r and theta, whose first component is r cosine theta, second component is r sine theta, third one is r run from 0 to 1, and theta run from 0 to 2 pi. Again, I already discussed in my last slides. So this is another what is called parameterizations. Again, look at the component of my phi. Again, it is very nice. So it is a functions of cosine and sine functions, or functions of r and theta. So it is differentiable, continuously differentiable. You can check that it is injective in the interior region of R, and you can also check that at any point P in R, the corresponding normal vector, that means del phi del R at the point P and del phi del theta at the point P, if I take the cross product, it will be a non-zero vector. You can just check it. So for each of the example, you can check it, and you will see all of the examples are what is called smooth surfaces. Okay, so now once I have a smooth surfaces, then one can calculate the normal vector to the smooth surfaces. So finding normal vector to the smooth surfaces. So let's suppose S is a smooth or piecewise smooth surfaces in R3. Suppose this is the corresponding parameterization is given where UV runs over R, and suppose R is very nice region in R2. That means suppose it is simple convex region in R2. Then what will be the corresponding normal vector to that smooth surfaces? So for that, what you have to do, once I have a parameterizations, what you do, first you consider the phi u, that means del phi del u. What is del phi del u? That means what are the components? That means this is del x del u, del y del u, del z del u, because a phi has a component x comma y comma z. So therefore del phi del u, so this is, you can say that this is del phi del u. So this is nothing but del x del u, del y del u, and del z del u. That is the first fact. What is del phi del v? So that means phi v means what? That means I am del phi del v. Again, actually I am talking about del phi del v at the point u comma v, though I have not written u comma v here, but it automatically means that I am talking about the partial derivative of phi with respect to u variable at the point u v. Okay, so that means del phi del u is this expression, del phi del v is this expression. So normal, I just said take the cross product any point. So phi u cross phi b, if I take, this is the kind of corresponding determinant formula. So that means first row should be ijk, second row should be component of phi u, and third row is the component of phi b, and use just determinant formula. Then the unit normal vector, which I denoted as n cap, to the surfaces S, and which is given by unit normal. So I am talking about the unit normal, so that means I am just normalizing it. What is that? This should be plus minus phi u cross phi b divided by norm of. So you can also write this norm of phi u cross phi b. Okay, so therefore you know the how to calculate the normal. So what you do, so first you get your smooth surfaces, that means get the parameterizations. Then what you do, you have to first consider del phi del u and del phi del v. So then if I just take the cross product and then the corresponding unit normal to my surfaces, which is nothing but that plus minus phi u cross phi b divided by norm of phi u cross phi b. So this is the unit normal vector. That plus minus depends actually whether I am talking about outward normal or inward normal. That depends on whether I am giving the plus sign or minus sign. If it is plus sign, that means I am talking about at that point, that means given ub, the parameterizations, the corresponding RUB is a point in surfaces. At that point, if I, whether the normal at that point or of ub, whether it is pointing outward directions, it depends on the plus sign, and inward direction, it depends on the minus sign. So that is why this is. Okay. So this is, that's how one can find the normal vector to my smooth surfaces once I have a smooth surfaces. Okay. This is another formula, finding normal to a smooth surfaces if it is given what is called the explicit representation. See, so suppose the surfaces S is defined in the equation Z is equal to G of xy. That means the representation, explicit representation of my surface is given. That means what are the points in the R3, x comma y, and Z, it is nothing but G of xy. If this is the case, where xy runs over R, where suppose R is a very nice region, that means horizontally or vertically simple convex region in the xy plane, that means my given surface is given by x comma y comma z, where xy runs over this nice region R and z is a function of G of xy. Then rewrite this parametric form. How do I write it? So you know, I already talked about, if I have a surfaces which is given in the explicit representation, then it will have a parametric representation. What is the parametric representation? This is phi. Okay, xy runs over the region R, where xy is in R, and what will be the values taking in R3? That means first is component is x, second component is y, and third component you just replace z by G of xy. So this is the corresponding what is called parametric representations, okay, for my surfaces. Then what you do? Then you have to calculate the corresponding del phi del x and del phi del y, and you just take the cross product and then normalize it. Okay, so that exactly I have done. Now if I calculate the del phi del x, now look at phi of xy is given x comma y comma this. So therefore del phi del x, that means you just take the partial derivative of each component with respect to x variable. First one will give you 1, second one will give you 0 because it is a function of y, and third one will give you del g del x, that means g partial derivative of g with respect to x. What about phi y? First one is, since it is a function of x, it will give you 0, second one will give you 1, and third one will give you del g del y. So now you have to take the cross product. This is the determinant formula. If you calculate it, it turns out that this vector is nothing but the first component should be minus gx, second component will be minus g, and third component will be 1. Okay. Now once I have the phi x cross phi y vector, then means if I calculate the norm, that means it turns out that this is nothing but square root of 1 plus del g del x square plus del g del y square. So that means what is the unit normal vector? Plus minus of del phi del x cross del phi del y divided by norm of del phi del x cross del phi del y, and it is the explicit representation in terms of g. Because you see, if I have a surface given is in an explicit representation, that means the function g is given. Once you know the functions of g, then you can calculate the unit normal vector n hat. And what is the formula? That means you have to calculate del g del x, del g del y. Okay, so you take the minus sign, so that means minus del g del x times I cap minus del g del y times j cap plus k cap, and then you just divide it by square root of 1 plus del g del x square plus del g del y square. That will give you the what is called unit normal vector n cap on my surfaces at the point what is called phi of xy. So given xy point in R2, then it will induce a point phi of xy in that surfaces. At that point my unit normal vector, whether it is outward or inward, it depends on the sign, but this is the formula, and that formula deals with the functions of g, because my surface is given the explicit representation, when the function g is given, then it is of the form x comma y comma z, and z is function of g of x comma y. So therefore in terms of g, it is, you can write the unit normal vector n cap. So and this is exactly this one. Okay, so this is means finding normal vector for a smooth surfaces if it has say what is called explicit representation. That means if you know the this relation z is equal to g of xy, then in terms of g, this is the corresponding what is called representations of unit normal vector. Okay, so this is another. So finding unit normal vector to smooth surface, it says that suppose your surface is identified with this kind of functions like g of x y z is equal to 0, right? So in that case, what will be your surface? That means it is the collection of all those x y z, or g of x y z, I mean it's satisfying some functional relations, right? So that means suppose g of x y z is equal to x square plus y square plus z square minus 1 is equal to 0. That means it is again unit sphere. So therefore it is given by functional equation. So that means it is the collection of all those x y z, where g of x comma y comma z is equal to 0. I am not saying that z can be written in terms of x1 y. I am not saying that. It is like some functions involve three variables x, y and z, and suppose it becomes 0, this will also give you a surface, right. So then what will be the corresponding normal, whether pointing outward. So what is that? Then I am written the normal pointing outward or positive normal to my surfaces. Then what you have to do now, since function is g is given, then it will have three partial derivatives. I can talk about del g del x, del g del y and del g del z. So that means the corresponding unit normal vector, what is that? You have to calculate the gradient, that means delta of g, plus minus sign depends whether I am talking about outward and inward, and then normalize means you have to divide by norm of delta g. And what is the gradient of g? This is nothing but del g del x, del g del y and del g del z divided by norm of delta g, which is nothing but square root of del g del x square plus del g del y square plus del g del z square. So therefore, if I have a surface which is given by this functional relation g of x y z is equal to 0, then the corresponding unit normal vector, I can have the formula. And what is the formula? This is the formula. So you first consider the gradient of my function g, that means del g del x, del g del y and del g del z. So you just so gx, nothing, I am talking about del g del x, okay, at the point x y z. And what is gy? Del g del y at the point x y z. And what is del g, gz, del g del z at the point x y z. So you know the function g, so you can calculate del g del x, del g del y and del g del z at the point x y z, and you just divide it by norm, and that will give you the what is called pointing outward. Okay, plus sign is there, that's why I am talking about pointing outward. If it is minus sign, it means pointing downward. Okay. Okay, so now as I said, so since I am already talked about like kind of unit normal vector, so now I can talk about what is called smooth surfaces in this way as well. What is that? So smooth surfaces I can talk about in terms of unit normal vector. Then we say that S is two-sided. That means if I have a surface, it should be two-sided. That means I should cross from one side to another side, crossing to the boundary. Then it is called the two-sided. It should be parametrized. And third one is that at each point P on the surface, you will have normal. You know how to calculate normal, I just checked. So the normal n hat of P should exist and it should be non-zero. Now look at this picture. So this picture actually says that I am at each point, it is the normal vector and it is pointing upward directions. So in the above picture, plus n hat of P is pointing outward or upward directions, whereas if I draw minus n hat P, it will be actually pointed inward direction. So therefore, smooth surfaces in terms of unit normal vector you can also define in this way. So smooth surfaces S means it should be two-sided. I mean it is not should be like Mobius strip, it's at only one surfaces. One surfaces has one side, not two-sided. Okay, so I do not want those kind of surfaces like Mobius map. Okay, Mobius like Mobius brand. So I do not want that kind of things. Okay, so I want a surface, it should be smooth. The definition I can think about the smooth surfaces S means the surfaces should have two-sided. That means I can come from one side to another side via boundary. Okay, that is one. So second one is that it should be parameterized. You know how to get the parameterizations. And third one, at each point P on my surfaces, the normal, that means n hat of P should be exist and it should be non-zero. Again, actually that is exactly given in the definition of smooth surfaces. Look what I define the so this is the corresponding parameterization, right? I want it should be continuously differentiable, it should be injective in the interior region of R, and at each point the normal vector should be non-zero. So same in terms, same definition it's there. Okay. Okay, so I think that is kind of notions of smooth surfaces. Now once I have the notions of smooth surfaces and the unit normal vector, how to calculate given the smooth surfaces or piecewise smooth surfaces, then I can talk about what is called oriented surface. And that surface, suppose you have a surface, you have a given orientations, then it will induce orientations to my boundary curve. Okay, maybe I think in my next class I will talk about that again. So because now I have the notions of surfaces and I have the notions of how to calculate the unit normal at the point on that surfaces. Once I have the smooth surface or piecewise smooth surface along with the unit normal vector, then I can talk about the orientation of the surfaces. Of course, this kind of things I already discussed in my earlier lectures. So but again it is the recalling part because I need those concepts to talk about the statement of Stokes theorem. So now I know smooth surfaces, I'm okay, and now I know the what is called unit normal vector, how to calculate in the given surfaces. So once I have a smooth surfaces and the notions of unit normal vector, then I can talk about what is called oriented surface. Once I have a oriented surface, then that oriented surface will induce a orientation on its boundary. That we can talk about it, that is positive orientation or negative orientation. So whatever suppose whatever surfaces it is given, it will have some orientations. I will talk about what do I mean by oriented surface. That will induce a orientation in the boundary. and I need those kind of concepts to when because I need to state the Stokes theorem. For that I need those orientations of the boundary. Okay. So, in my next lecture I will start with the orientations of my surfaces, and then I will tell you that the orientations, given orientations of the surfaces will induce orientations on the boundary of the surfaces, and then I will talk about the statement of Stokes theorem and some example I will talk about. Maybe I think I will start in the next lecture the oriented surface. I think I should stop here today. Thank you.